The human brain alone contains about 100 billion nerve cells, called neurons. A neuron, like every other cell, has positively and negatively charged ions, inside and outside. Further, a resting neuron has a greater negative charge on the inside surface of the plasma membrane and a greater positive charge on the outside surface. This partitioning of charge creates a voltage difference across the membrane known as the resting membrane potential, which can be measured using a voltmeter. On average, an intracellular electrode records a value of minus 70 millivolts. The resting membrane potential depends on two factors. First, it depends on the presence of sodium and potassium gradients across the plasma membrane. Specifically, there are more sodium ions outside the neuron than inside, and more potassium ions inside the neuron than outside. Second, the resting membrane potential depends on the differential permeability of the plasma membrane to sodium and potassium ions. Leak channels in the plasma membrane allow sodium and potassium ions to diffuse or leak down their concentration gradients. The membrane contains many more potassium leak channels than sodium leak channels. Thus, the membrane is much more permeable, or leaky, to potassium ions. As positively charged potassium ions leak out of the neuron, the inside surface of the membrane becomes negatively charged compared to the outside surface. If potassium was the only ion moving, the potential would stabilize at minus 90 millivolts. However, positively charged sodium ions leak into the neuron, which slightly offsets the negative charge and raises the voltmeter reading to minus 70 millivolts. Sodium-potassium pumps actively transport sodium ions out of the neuron and potassium ions back in, compensating for the sodium and potassium leaks. Thus, the pumps help to maintain the resting membrane potential.